Your city is buried in snow right now, and you've been told it's because of something called a polar vortex. But here's what they're not telling you. On January 18th, 2026, the sun threw a punch at Earth so hard it registered as one of the top 5 radiation storms since the 1970s. 10,000 times the normal particle flux. A magnetic field spike that nearly triggered Carrington-level chaos. And it happened the exact moment the polar vortex started to shatter. Meteorologists won't connect these dots. They can't, or they won't. But by the end of this video, you'll understand why your winter didn't start in the Arctic. It started 93 million miles away. And you'll see why this might just be the beginning. Subscribe and follow along, because what unfolds in the coming weeks will determine whether this storm was a freak alignment or evidence that we've been ignoring a connection between space and weather that's been there all along. Because when a solar radiation storm, a collapsing polar vortex, and atmospheric instability converge to paralyze multiple continents simultaneously in ways we've never seen before, that's not coincidence. That's a warning we weren't equipped to recognize. You probably remember where you were when the power went out. Maybe you were sitting in your living room in Houston when the lights flickered and died. Maybe you were watching the news from London as blizzards shut down 90% of the country. Maybe you stepped outside one morning in Sapporo and couldn't believe how much snow had fallen overnight. What you probably don't remember is January 18th, 2026. That's the day winter actually began, and it didn't start in the Arctic. It started on the surface of the sun. On that day, monitoring stations around the world detected something that made solar physicists sit up straight in their chairs. A long-duration X 1.9 solar flare erupted from the sun's surface. And when I say long duration, I don't mean a brief flash of energy. This thing kept pumping radiation into space for hours. X-class flares are the heavyweight champions of solar events, the top tier of what the sun can throw at us. But it's not just about the letter grade. Long-duration events inject vastly more energy into the space between the sun and Earth. They're not just bright, they're persistent. They're the difference between a camera flash and a floodlight that won't turn off. Within hours, something else started happening. An S4 radiation storm, the second highest category on the scale, began pummeling Earth's magnetosphere. The proton flux, the measure of how many high-energy particles are streaming through space, increased roughly 10,000 times above baseline levels. Let me put that in perspective. Normal space weather is like standing in a light drizzle. This was like standing under Niagara Falls. The last time we saw a radiation storm this strong was October 2003, 23 years ago. Since scientists began systematic monitoring in the 1970s, this ranks in the top 4 or 5 radiation events ever recorded. This wasn't just unusual. This was generational. But the solar flare and radiation storm were only the opening act. What followed was a G4 geomagnetic storm, one step below the most extreme classification possible. The KP index, which measures geomagnetic disturbance on a scale from 0 to 9, peaked at 8.67. For context, anything above 8 qualifies as a G5 event, the kind of storm that can knock out power grids and fry transformers. We were inches away from that threshold. The interplanetary magnetic field, the invisible force that extends from the sun and wraps around Earth, spiked near 90 nanotesla. On a calm day, that number sits around 5. During severe storms, it might hit 30 or 50. 90 nanotesla is off the charts. It's the kind of number that makes scientists double-check their instruments. Here's where it gets interesting. Earth got lucky, sort of. The magnetic polarity of the storm was positive, which means the way it coupled with Earth's own magnetic field was less efficient than it could have been. If that polarity had been reversed, if the magnetic orientation had lined up differently, scientists believe we could have seen Carrington-level impacts. The Carrington event of 1859 was the most powerful geomagnetic storm in recorded history. Telegraph systems caught fire. Auroras were visible in the Caribbean. If something like that happened today, with our dependence on satellites, GPS, and interconnected power grids, the economic damage would be measured in trillions of dollars. We came closer to that scenario than most people realize. The night sky told a different story than the news reports. Auroras appeared at latitudes where they're almost never seen, shimmering curtains of green and red light dancing over regions far from the poles. In parts of Europe, people reported a strange chemiluminescent afterglow, a faint greenish glow that lingered in the sky long after the main auroral display had faded. This wasn't just pretty. This was visible evidence of massive energy deposition into the upper atmosphere. The sky was literally glowing with excess energy that had nowhere else to go. And here's the part that should disturb you. The media coverage that week focused almost entirely on snowstorms and power outages. There were breathless reports about blizzards in Texas, historic cold in Europe, unprecedented snowfall in Japan. What there wasn't was any meaningful discussion of the solar storm. Virtually no major news outlet mentioned that one of the strongest radiation storms in nearly a quarter century had just slammed into our planet. The silence was deafening. It was as if two different events were happening simultaneously, one in space and one on the ground, and nobody was connecting the dots. So let me ask you the question that's going to drive everything that follows. If this was genuinely one of the strongest radiation storms in 23 years, ranking in the top handful of events since systematic monitoring began, why wasn't it treated like one? Why wasn't there wall-to-wall coverage? Why weren't scientists appearing on morning news shows to explain what had just happened? The answer, I think, is uncomfortable, because what this storm may have done didn't stop in space. What it may have done was reach down into our atmosphere and break something that meteorologists thought was independent of the sun. What it may have done was trigger the most extreme winter weather event in a generation. And if that's true, everything we think we know about predicting winter storms needs to be rewritten. Because what happened next didn't unfold over months. It happened in days, and it happened in a way that shouldn't have been possible. Space weather doesn't create storms out of nothing. That's not how this works. The atmosphere is far too massive, far too complex, for a few hours of solar radiation to suddenly manufacture a blizzard from clear skies. But what if space weather doesn't need to create storms? What if it just needs to amplify systems that are already unstable, already teetering on the edge of chaos? What if the solar storm of January 18th didn't cause the polar vortex collapse, but instead acted like a finger pressing on a crack in a dam? Let's start with timing, because timing is everything in this story. In mid-January 2026, the polar vortex was already showing signs of weakness. For those unfamiliar, the polar vortex is a massive band of low-pressure air that circles the Arctic during winter, spinning counterclockwise and acting like a fence that keeps Arctic air bottled up over the North Pole. When that fence weakens or breaks, Arctic air spills southward, bringing extreme cold to regions that aren't prepared for it. Meteorologists had been watching the vortex wobble for weeks. It was unstable, but not yet broken. Then the solar storm hit, and within days, the vortex didn't just weaken, it shattered. Here's where location becomes critical. Solar radiation doesn't hit Earth uniformly. Energetic particles from the sun follow the planet's magnetic field lines, like cars following highway lanes, and those field lines funnel through specific entry points called magnetic polar cusps. These cusps are located near the poles, and here's the strange coincidence that nobody seems to want to talk about. Earth's northern magnetic pole has been drifting for decades, moving away from Canada and towards Siberia. In 2026, that magnetic pole sits unusually close to the geographic North Pole, closer than it's been in modern records, which means solar particles are being funneled directly into the region where the polar vortex circulates. The polar vortex isn't just a tropospheric phenomenon, confined to the lower atmosphere where weather happens. It extends upward into the stratosphere, reaching altitudes around 50 kilometers above the surface. That's the same altitude range where energetic particles from solar storms deposit their energy. When a high-energy proton from the sun slams into the thin air at that height, it doesn't just stop. It creates an ionization cascade, a chain reaction where one particle generates thousands of secondary interactions. Electrons are stripped from molecules. Chemical bonds break and reform. The local conductivity of the atmosphere changes. The electrical properties of the upper atmosphere are suddenly different than they were an hour ago. Now, most people don't think of the atmosphere as an electrical system. We think of it as a fluid, governed by temperature and pressure and the rotation of the Earth. But the atmosphere is also a massive electrical circuit. Storm systems rely partly on charge separation, the buildup of positive and negative charges in different regions of a cloud. Lightning is just the most visible manifestation of this. The moment when the electrical potential becomes so large that air itself becomes a conductor. But even without lightning, there's always a background electrical field. Ice crystals and clouds gain electrical charge through collisions. Water droplets do the same. The global electrical circuit, the sum of all these tiny charges across the entire planet, is always humming in the background. Here's the hypothesis, and I want to be clear that this is a hypothesis, not established fact. If the solar radiation storm enhanced the global electrical circuit, if it increased the baseline conductivity and charge density in the upper atmosphere, it could have intensified winter storms in ways that meteorological models don't account for. Ice storms could have formed more rapidly. Thundersnow, a rare phenomenon where lightning occurs during snowfall, could have become more common. The energy that drives weather comes primarily from the sun's heat. But what if electrical energy, normally a minor player, suddenly became significant? What if the storms of late January 2026 were electrically supercharged in a way we've never seen before? The signature of what happened next is unmistakable. The polar vortex didn't just weaken. It split into two separate lobes, like a cell dividing. One lobe drifted over Europe. The other settled over North America. And here's the truly bizarre part. While the vortex lobes brought Arctic air crashing southward into the mid-latitudes, the Arctic itself warmed up. Temperatures over the North Pole spiked well above freezing in some regions. The Arctic was warm while Texas was freezing. The weather map looked upside down. Meteorology can explain how a vortex split happens through wave dynamics and atmospheric pressure patterns. What it struggles to explain is why this particular split was so violent, so rapid, and so persistent. Why didn't the vortex just wobble and reform the way it usually does? Why did it stay broken for weeks? The real-world impacts were immediate and overwhelming. Texas experienced its coldest temperatures in decades, with ice storms that paralyzed Houston and Dallas. Europe saw simultaneous cold outbreaks that blanketed the UK and knocked out power across France and Germany. Japan reported some of the heaviest snowfall around Sapporo in years. Kamchatka, already accustomed to brutal winters, measured snow accumulations that broke 60-year records. This wasn't one region experiencing unusual weather. This was multiple continents, on opposite sides of the world, all experiencing extreme winter conditions in the same week. The question meteorologists couldn't answer was simple. Why all at once? Why everywhere? The conventional explanation is that polar vortex disruptions cause widespread cold outbreaks, and that's true. But previous vortex disruptions didn't produce this level of simultaneity or severity. Something about this event was different. The storms were more intense. The cold was more persistent. The infrastructure failures were more widespread. Meteorology can tell us how the vortex split. It can show us the pressure gradients and the Rossby waves and all the atmospheric mechanics that moved cold air southward. What it doesn't answer is the deeper question. Why did an already unstable vortex suddenly collapse with such force precisely when the strongest radiation storm in 23 years was bombarding the polar regions? Coincidence is possible. But the data suggests something more troubling. The data suggests amplification. And if that's true, the real evidence isn't in computer models or atmospheric simulations. The real evidence is on the ground, in the snow and ice, and the strange electrical phenomena that nobody can quite explain. Because what happened in late January 2026 wasn't just extreme cold. It was weird. And weird is often a signal that something fundamental has changed. Numbers can't quite capture what it felt like on the ground, but let me try. 40 US states reported winter weather impacts in the span of 1 week. More than 1 million people lost power, some for days. In the South, where infrastructure isn't built for prolonged freezing, water pipes burst in cities across Texas, Louisiana, Mississippi, and Alabama. Emergency rooms filled with people suffering from hypothermia and carbon monoxide poisoning from improper heating. The death toll climbed into the dozens. Then the hundreds, as the full scope became clear. This wasn't just inconvenient weather. This was a humanitarian crisis unfolding in one of the wealthiest nations on Earth. The international scope was equally staggering. The Kamchatka Peninsula in far eastern Russia, a place where winter is always brutal, measured its heaviest snowfall in 60 years. Residents reported snow accumulations so deep that buildings were buried to their rooflines. In Japan, the Sapporo region saw historic snowfall that paralyzed transportation and left tens of thousands stranded. The UK experienced what meteorologists described as the worst blizzard in decades, with snow and ice affecting roughly 90% of the country. Roads became impassable, trains stopped running, airports shut down. Europe, which prides itself on resilient infrastructure, was brought to its knees by weather that seemed to come out of nowhere. But here's what made this different from previous cold snaps. In many southern US regions, it wasn't snow that caused the worst damage. It was ice. Specifically, freezing rain and sleet, precipitation that falls as liquid but freezes on contact with the ground. Ice storms are uniquely destructive. A quarter inch of ice can snap tree branches. Half an inch can bring down power lines. An inch can collapse structures. Houston, San Antonio, and New Orleans weren't dealing with fluffy snow that could be plowed. They were dealing with a coating of ice that turned every surface into a skating rink and every road into a death trap. Emergency vehicles couldn't respond. People couldn't get to work. The entire region ground to a halt. And then there were the anomalies. Reports started coming in from South Texas of something meteorologists almost never see in ice storms: thundersnow. Thunder and lightning during frozen precipitation. For those unfamiliar, thundersnow is extremely rare because the conditions that produce lightning, strong updrafts, and significant electrical charge separation are usually suppressed in winter storms. Cold air is denser and more stable than warm air. It doesn't rise as readily. Winter storms are typically quieter, electrically speaking, than summer thunderstorms. And yet, multiple reports from San Antonio, Austin, and surrounding areas described brilliant flashes of light and booming thunder in the middle of ice storms. Some witnesses reported lightning striking during periods of heavy sleet, an almost unheard of combination. Why does this matter? Because lightning doesn't just happen randomly. It requires strong electrical gradients, a significant difference in charge between the cloud and the ground, or between different parts of the cloud. The fact that thundersnow occurred during what should have been electrically quiet ice storms suggests something unusual was happening with atmospheric electricity. The hypothesis, and again I'm labeling this clearly as speculation, is that elevated atmospheric electrical charge from the solar particle influx increased the electrical potential in storm systems. The storms didn't need to develop strong updrafts to generate lightning. The baseline charge was already elevated. The atmosphere was primed for electrical discharge in a way it normally isn't during winter. there was another visible anomaly that most people missed. In the days following the main storm, people across northern latitudes reported a strange green glow in the night sky. This wasn't the aurora, which is caused by particles hitting the atmosphere in real time. This was a persistent afterglow, a faint luminescence that appeared even on nights when there was no solar activity. Scientists call this chemiluminescence, the slow release of energy stored in the upper atmosphere during the storm. Certain molecules, particularly oxygen and nitrogen, can remain in excited states for hours or even days after the initial energy input. When they finally relax back to their ground state, they emit light. That green glow people saw wasn't just pretty. It was evidence that massive amounts of energy had been dumped into the atmosphere and were still leaking out days later. The simultaneity of impacts across multiple continents is what keeps me up at night. If this were just a random polar vortex disruption, you'd expect regional variations in timing and severity. Instead, we saw extreme weather hitting North America, Europe, and Asia in the same week, driven by the same atmospheric pattern. The odds of that happening by pure chance aren't zero, but they're not high either. Meteorologists point to the split vortex as the cause, and they're not wrong. But that's a description, not an explanation. It's like saying a building collapsed because the support beams failed. Sure, but why did the support beams fail at that exact moment? What was the trigger? Let me be clear about what I'm not saying. I'm not claiming that the solar storm created the winter weather out of nothing. I'm not suggesting that space weather can override the fundamental physics of atmospheric circulation. What I am saying is that the timing, the severity, and the strange electrical phenomena all point to something beyond a routine vortex disruption. The solar storm may have acted as an amplifier, taking a system that was already unstable and pushing it into a more extreme state than it would have reached on its own. The question isn't whether the vortex would have collapsed eventually. The question is whether it would have collapsed this violently, this quickly, and with these unusual characteristics without the solar influence. And if you think this is all speculation, if you think I'm drawing connections that don't exist, ask yourself this. Why did so many independent systems fail at once? Why did infrastructure in Texas, Europe, and Japan all prove inadequate in the same week? Random coincidence is possible, but the alternative, that we experienced external amplification of an already dangerous weather pattern, is at least worth considering. Because if that's what happened, the implications are uncomfortable. It means our weather isn't as independent from space as we thought. It means prediction becomes vastly more complicated. And it means what happened in January 2026 might not be a one-time event. It might be a preview of a new kind of winter, one where the sun plays a role we've never accounted for. And that possibility, that uncomfortable uncertainty, is where the real controversy begins. Let me tell you about two scientific communities that exist in separate worlds. On one side, you have meteorologists, people who study the troposphere and lower stratosphere, who build forecast models based on temperature, pressure, humidity, and wind patterns. They can predict a hurricane's path 3 days out with remarkable accuracy. They can tell you when a cold front will arrive and how much snow to expect. Their tools are sophisticated, their models constantly refined. On the other side, you have space weather scientists, people who study the magnetosphere, the ionosphere, the solar wind, and geomagnetic storms. They can tell you when a coronal mass ejection will reach Earth and what the KP index will be. They track particle flux and magnetic field strength. And here's the problem. These two communities rarely talk to each other. They attend different conferences. They publish in different journals. They use different vocabulary. When a meteorologist builds a winter forecast model, it doesn't include solar radiation storms. When a space physicist models the magnetosphere, it doesn't include tropospheric dynamics. The wall between these disciplines isn't hostile. It's just institutional inertia. and that wall might be blinding us to connections that matter. Why don't weather forecast models include solar radiation storms? The answer is practical, not conspiratorial. Weather models operate on short timescales, typically 7 to 10 days out, sometimes 2 weeks for seasonal predictions. Solar storms, while trackable, are hard to predict with precision more than a few days in advance. Adding solar parameters to weather models would require computational resources that most meteorological centers don't have. The models are already running at the edge of what's computationally feasible. Adding another layer of complexity, especially for a factor that historically hasn't shown strong impacts on surface weather, doesn't make sense from a resource allocation perspective. But what if that historical assumption is wrong? What if solar storms do affect surface weather under certain conditions, and we've just never had the data resolution to see it clearly? There's also a deeper issue. The mainstream meteorological community isn't ignoring the solar storm. They're treating it as irrelevant. If you read the official analyses of the late January 2026 weather events, you'll find detailed discussions of the polar vortex dynamics, the stratospheric warming, the pressure gradients. What you won't find is a single mention of the X1.9 flare, or the S4 radiation storm, or the G4 geomagnetic storm. It's not that meteorologists don't know these things happened. It's that they don't believe they matter for tropospheric weather. And they have a point. Correlation doesn't equal causation. Polar vortex disruptions have happened many times before without simultaneous major solar storms. The fact that these two events occurred together could be pure coincidence. The burden of proof is on anyone claiming a connection to show a physical mechanism, not just timing. But here's where it gets uncomfortable. When you ask meteorologists directly about the possibility of solar influence, many will acknowledge that it's theoretically possible, but practically unproven. Some will point to studies showing weak correlations between solar activity and certain weather patterns. Others will dismiss the whole idea as fringe science, lumping it in with astrology and other forms of magical thinking. The problem is that absence of evidence isn't evidence of absence. Just because we haven't proven a strong solar weather connection doesn't mean it doesn't exist. It might just mean we haven't looked carefully enough, or that our instruments aren't sensitive enough to detect subtle effects. There's also a narrative tension around climate science that makes this conversation difficult. Over the past few decades, scientists have built a robust case that human-caused climate change is warming the planet and altering weather patterns. That case is based on physics, observations, and modeling. It's not controversial within the scientific community, but when you start talking about solar influence on weather, you enter politically charged territory. Climate skeptics have long pointed to the sun as an alternative explanation for warming, usually incorrectly. The sun's total energy output does vary slightly over an 11-year cycle, but those variations are far too small to explain the warming we've observed. So when legitimate scientists explore possible solar influences on specific weather events, they risk being misinterpreted as questioning the climate consensus. That's not what's happening here. Nobody is suggesting the sun caused global warming. The question is whether intense solar storms can temporarily amplify weather patterns that are already in motion. That's a much narrower, much more specific claim. But nuance gets lost in polarized debates. Media incentives also play a role. Ground impacts are easy to explain. You can show footage of people slipping on ice, cars stranded on highways, power lines down. It's visceral. It's immediate. Solar physics, on the other hand, is abstract. Try explaining ionization cascades and magnetospheric coupling to a general audience in a 30-second news segment. It's hard. It requires graphics and analogies and patience. Most news outlets don't have the resources or the interest to dive that deep, so they stick with what's straightforward. Polar vortex disrupts. Cold air moves south. Snowstorms result. Simple. Clean. Done. The solar storm, if it's mentioned at all, gets a throwaway line about pretty auroras. The possibility that it influenced the weather? That's too speculative, too complicated, too likely to confuse viewers. Was the public shielded from this information to avoid panic? I don't think so. I don't believe there was any coordinated effort to hide the solar storm or its potential impacts. What I do think happened is a combination of institutional silos, risk aversion, and genuine uncertainty. Meteorologists focused on what they know, atmospheric dynamics. Space weather scientists focused on what they know, geomagnetic impacts on satellites and power grids. Nobody was explicitly looking at the intersection. Nobody had a mandate to connect those dots. And when something falls into the gap between disciplines, it often just gets missed. Not maliciously, just structurally. But here's the uncomfortable truth that nobody wants to say out loud. If solar storms can significantly affect weather, even occasionally, even under specific conditions, our ability to predict extreme weather becomes vastly more complicated. Right now, meteorologists can issue a winter storm warning 3 to 5 days out with reasonable confidence. But if they also need to account for solar activity, and if solar storms are only reliably predictable a day or two in advance, that prediction window shrinks. Uncertainty expands. And in a world where people rely on weather forecasts for everything from travel plans to disaster preparedness, increased uncertainty has real costs. It's easier, psychologically and institutionally, to operate under the assumption that weather is weather and space is space, and never the twain shall meet. Challenging that assumption opens a can of worms that many people would rather leave closed, and yet the data won't leave us alone. The timing was too precise, the impacts were too widespread, the anomalies were too consistent. You can dismiss one or two strange observations as noise, but when multiple independent lines of evidence all point in the same direction, at some point you have to take it seriously. At some point you have to ask whether the old assumptions still hold. And that brings us to the really disturbing possibility. What if January 2026 wasn't a one-time event? What if the solar storm did more than just amplify a single weather pattern? What if it changed the baseline conditions of Earth's near-space environment in ways that persist? Because space weather doesn't just affect us in the moment. It can reshape the very structure of the space around our planet. And those changes can last for years. Most people think of space as empty, but the region around Earth is anything but. Our planet is surrounded by invisible donuts of trapped radiation called the Van Allen belts, named after the physicist who discovered them in 1958. There's an inner belt, starting about 600 miles up, full of high-energy protons. There's an outer belt, farther out, dominated by electrons. These belts trap energetic particles from the solar wind and cosmic rays, holding them in a magnetic cage that rotates with Earth. Satellites passing through these belts get bombarded with radiation. The particles can damage electronics, degrade solar panels, and pose risks to astronauts. Space agencies track the radiation belts obsessively because knowing their structure is critical for mission planning. But here's what most people don't realize. The radiation belts aren't static. They change. Strong geomagnetic storms can inject new particles, creating additional belts or enhancing existing ones. And sometimes those changes persist. The Halloween storms of 2003, a series of powerful solar events similar in magnitude to what we saw in January 2026, created a new radiation belt that persisted for years. Observations from satellites showed enhanced particle populations that didn't dissipate for months. The near-Earth space environment was fundamentally altered. And during that period, satellite failures increased. Communication disruptions became more common. The baseline conditions were different. Could the January 2026 storm have done something similar? The data isn't all in yet, but early indications suggest yes. The S4 radiation storm pumped enormous numbers of energetic protons into Earth's magnetosphere. Some of those particles got trapped. Others spiraled along magnetic field lines, penetrating deeper into the atmosphere than usual. The magnetosphere was compressed, squeezed like a sponge by the intense solar wind pressure. When that happens, something called plasmasphere erosion can occur. The plasmasphere is a region of relatively dense, cold plasma that corrotates with Earth, acting like a shield that deflects incoming particles. When the magnetosphere gets compressed, the plasmasphere can be stripped away, allowing energetic particles to penetrate closer to the planet. That erosion doesn't instantly repair itself when the storm ends. It takes time for the plasmasphere to refill, days, sometimes weeks. And during that recovery period, the baseline conditions are different. Particles that normally wouldn't reach certain altitudes can suddenly get there. The atmospheric ionization rate increases. The electrical properties of the upper atmosphere shift. The hypothesis, and I'm going to keep emphasizing that this is still a hypothesis, is that the January 2026 storm altered Earth's near-space environment in ways that persisted beyond the initial event. The proton flux remained elevated for roughly a week, far longer than typical solar events. The magnetospheric energy, the total amount of stored energy in Earth's magnetic field, took days to dissipate. And during that entire period, the polar vortex was wobbling, splitting, behaving erratically. Each subsequent wobble occurred in atmospheric conditions that were electrically different than normal. It's possible, maybe even likely, that the storm created a feedback loop. The initial disruption weakened the vortex. The ongoing elevated particle flux and altered magnetospheric conditions kept it destabilized. What should have been a brief disruption became a prolonged collapse. Why does this matter for the rest of winter 2026? Because if the near-Earth space environment is still altered, if the radiation belts are still enhanced, if the plasmasphere is still partially eroded, then every weather system that forms over the next few months is forming in conditions that are subtly different than normal. Think of it like changing the baseline charge on a battery. The battery still works, but now it delivers a little more voltage every time you use it. The atmosphere still produces winter storms, but now there's a little more electrical potential every time a storm system develops. The storms might be more intense. The charge separation might be more pronounced. Thundersnow might become more common. Ice storms might develop more rapidly. None of this is certain, but the possibility is there. And if it's real, winter 2026 might not be over. It might just be getting started. Let me paint some speculative scenarios, and I want to be very clear that these are speculative. If the magnetospheric conditions remain altered through February and March, we could see more frequent polar vortex disruptions. The vortex might try to reform and then collapse again. Each collapse would send another pulse of Arctic air southward, producing additional cold snaps. Or we could see longer duration cold spells. Instead of a week of extreme cold followed by a return to normal, we might see 2 weeks, 3 weeks of persistent below average temperatures. The infrastructure impacts would compound. Power grids that barely survived the first round would face repeated stress. Water systems would experience more freeze-thaw cycles. Transportation networks would struggle to recover. There's also the possibility of stronger electrical storms. If the atmospheric electrical circuit remains enhanced, winter thunderstorms could become more common and more severe. Lightning and snowstorms, ice storms with thunder. These aren't normal winter phenomena. They're signs that something fundamental has shifted, and they could pose hazards that emergency managers aren't prepared for. Fire departments responding to winter structure fires caused by lightning strikes. Search and rescue teams dealing with people injured by ice-coated power lines that are still electrically energized. These are scenarios that don't appear in standard winter preparedness plans. The historical analogs suggest caution. After the 2003 Halloween storms, space weather researchers noted increased satellite anomalies for months, communication disruptions, GPS errors, power grid fluctuations. The impacts weren't constant, but they were persistent. Little reminders that the space environment hadn't fully returned to normal. If we're in a similar situation now, if January 2026 created changes that will persist for months, then every industry that depends on space-based infrastructure needs to be on high alert. Airlines relying on GPS for navigation, shipping companies using satellite communications, financial institutions depending on precise timing signals. All of it could be affected by ongoing magnetospheric disturbances. And then there's the really unsettling possibility. What if this isn't just about one storm? What if we're entering a new regime where solar weather coupling is stronger than it used to be? Earth's magnetic field has been weakening gradually over the past century. The northern magnetic pole has been drifting faster than at any time in recorded history. These changes could make Earth more vulnerable to solar storms. A radiation storm that would have been deflected or absorbed harmlessly 50 years ago might now penetrate deeper, couple more efficiently, produce stronger ground-level impacts. If that's true, the storms of January 2026 aren't an anomaly. They're a preview. They're showing us what winters might look like in a world where the sun's influence on our weather can no longer be ignored. And the terrifying part? The storm that hit us in January wasn't even particularly large by historical standards. It was strong, yes, but not Carrington level. If a truly extreme solar storm hits while Earth's magnetic field is in a weakened state and the polar vortex is already unstable, the impacts could dwarf what we saw. We might not be talking about power outages and ice storms. We might be talking about societal disruption on a scale we haven't experienced in modern times. The storm may be over. The solar event concluded. The radiation flux returned to normal. The magnetosphere began to recover. But the effects? The effects may not be over at all. They might be echoing through the atmosphere, quietly reshaping the conditions under which winter weather develops. And we might not realize the full scope until months from now, when we look back at the data and see patterns that shouldn't be there. Strange correlations, anomalous intensities, signs that something changed in late January and never quite changed back. Scientists are watching. Make no mistake about that. The January 2026 event didn't go unnoticed in the space weather community. Monitoring stations around the world lit up with data. Solar observatories tracked the flare's evolution in real time. Magnetometers measured the interplanetary magnetic field as the storm swept past Earth. Radiation detectors on satellites recorded the proton flux minute by minute. Researchers pulled all-nighters, checking instruments, validating data, trying to understand what they were seeing. The observations were extraordinary. The X 1.9 flare itself was impressive, but what really caught attention was the persistence. The radiation storm didn't spike and fade, and it built gradually, sustained itself, and then declined slowly over days. That's unusual. Most solar events are sharp and brief. This one lingered. But here's the limit. We can see storms coming. We have satellites positioned between the Sun and Earth specifically to give us advance warning. When a coronal mass ejection erupts, we can detect it and calculate when it will arrive at Earth, usually with about 12 to 24 hours of lead time. We can measure the magnetic field orientation, estimate the likely strength of the geomagnetic storm, and issue warnings to power companies and satellite operators. What we can't do, at least not yet, is predict the full impact on Earth's atmosphere and weather systems. We don't have models that accurately translate space weather inputs into tropospheric outputs. The coupling mechanisms are too complex, too nonlinear, too poorly understood. We're flying blind in the most critical part of the chain. The January 2026 storm pushed instruments to their limits in ways that are still being analyzed. The interplanetary magnetic field reached values that are almost never observed outside of extreme events. The solar wind speed spiked above 700 kilometers per second, fast enough to compress Earth's magnetosphere to a fraction of its normal size. Some instruments designed to measure particle flux actually saturated, meaning the count rate was so high that the detectors couldn't keep up. Scientists had to use secondary calibrations and cross-reference multiple satellites to reconstruct what actually happened. The data is good, but it's at the edge of what our current instruments can handle. If we want to understand these events better, we need better sensors, more of them, positioned in more locations. We need a denser observational network. And there's growing recognition that we need something else. We need coupling models. Models that bridge the gap between space weather and terrestrial weather. A few research groups have been working on this for years, mostly in academic settings, without much funding or institutional support. Their models are crude, simplified, full of assumptions. But they're a start. They attempt to take solar wind parameters, magnetospheric conditions, and particle precipitation rates and translate them into atmospheric impacts, ionization rates, conductivity changes, electrical field modifications. And then, in principle, you could feed those outputs into a weather model and see what happens. Does the polar vortex respond? Do storms intensify? Does precipitation change? The goal is ambitious. The execution is still years away. But the interest is there now in a way it wasn't before January. Why does this matter? Because our technological dependence has never been higher. We have more satellites in orbit than ever before. GPS systems guide everything from commercial aviation to precision agriculture. Power grids are interconnected across vast regions, which improves efficiency but also creates vulnerabilities. A geomagnetic storm that induces currents in high-voltage transmission lines can cascade, knocking out power across entire states or countries. We saw hints of this in January, localized power failures that seemed disproportionate to the ground-level weather. Were those purely weather-related, or did geomagnetically induced currents play a role? We don't know because we weren't looking for it. Nobody was checking the magnetometer data and correlating it with transformer failures. That's the kind of blind spot that can cost billions of dollars and endanger lives. Solar Cycle 25, the current 11-year cycle of solar activity, is past its peak but still capable of producing major storms. The descending phase of a solar cycle can be particularly dangerous because large isolated events can occur unpredictably. The sun doesn't follow a smooth curve, it lurches, and the magnetic field configurations during the declining phase can sometimes produce storms that are more geo-effective, meaning they couple more efficiently with Earth's magnetosphere. We might not be out of the woods yet. The next 6 to 12 months could bring additional major solar events. And if they do, the question won't just be whether they disrupt satellites and power grids. The question will be whether they influence our weather in ways we're only beginning to understand. There's also a worst-case scenario that keeps space weather scientists up at night. What if a truly extreme storm hits? A once-in-a-century event like the Carrington storm of 1859, but with one additional factor that makes it worse. What if the magnetic polarity is reversed from what we saw in January? The positive polarity of the January storm reduced the coupling efficiency. But if the next major storm arrives with negative polarity, if the magnetic field orientation lines up perfectly with Earth's magnetosphere, the impacts could be catastrophic. Not just auroras and power outages. Wholesale grid failure, satellite constellations knocked offline, communication networks severed. And if that happens during an already unstable polar vortex, if the timing aligns the way it did in January, but with an order of magnitude more energy, we could see weather impacts that make January look mild. Simultaneous infrastructure failure and extreme weather across multiple continents. Emergency response systems overwhelmed. Supply chains disrupted. It's not a scenario anyone wants to contemplate, but it's a scenario we need to prepare for. The urgency is there. The technology is almost there. What's lagging is the institutional structure and funding to make it happen. Space weather research is chronically underfunded compared to other areas of atmospheric science. There are more scientists studying hurricanes than studying geomagnetic storms, even though the potential economic impacts are comparable. That needs to change. We need more monitoring satellites. We need better models. We need interdisciplinary teams where meteorologists and space physicists work together instead of in separate silos. We need real-time data sharing and coordinated warning systems. And we need a public that understands that space weather is real, that it affects daily life, and that ignoring it because it's invisible and abstract is a mistake. Because the next breakthrough in understanding these connections might not come from traditional science at all. It might come from somewhere unexpected, from tools and approaches that didn't exist a decade ago. It might come from artificial intelligence. Pattern recognition has always been humanity's superpower. We see faces in clouds. We hear music and noise. We find constellations in random star fields. Our brains are wired to detect patterns, to extrapolate from limited data, to make predictions based on past experience. But we're also limited. We can only hold so many variables in our heads at once. We struggle with high-dimensional data. We're bad at detecting subtle, nonlinear correlations buried in noise. And that's where artificial intelligence comes in. Machine learning algorithms, particularly deep neural networks, excel at exactly the things humans struggle with. They can process millions of data points simultaneously. They can detect patterns that are invisible to human intuition. They can learn from sparse, noisy data and make predictions that outperform traditional methods. And in the context of solar terrestrial physics, that capability might be revolutionary. Astronomers and space physicists are already using AI to analyze satellite data, identify solar flares before they peak, and predict geomagnetic storm intensity. Some algorithms can forecast the KP index hours in advance with accuracy that rivals traditional physics-based models. They do this not by solving equations, but by learning patterns from decades of historical data. The AI doesn't know why a certain combination of solar wind speed, magnetic field orientation, and particle density leads to a strong geomagnetic storm. It just knows that in the past, when those conditions occurred, a strong storm usually followed. And that's often enough. Prediction doesn't require understanding, at least not in the traditional sense. It requires recognizing patterns and projecting them forward. Now imagine applying that same approach to the solar weather connection. You'd need a training dataset that includes solar parameters, magnetospheric conditions, atmospheric measurements, and weather outcomes. That data exists, at least partially. Decades of satellite observations, ground-based magnetometer networks, weather station records. The problem is that nobody has assembled it all into a unified database and trained an AI model to look for correlations. It's a massive data engineering challenge. Different datasets use different formats. Temporal resolutions don't always match. Some data is public, some is proprietary. Some is archived in obscure formats that require specialized software to read. Bringing it all together would take years of effort and significant funding. But if someone did it, the results could be transformative. An AI trained on comprehensive solar weather data might detect precursors that humans miss. It might learn that when solar wind density exceeds a certain threshold, while the interplanetary magnetic field is oriented a certain way, and the stratospheric temperature gradient is within a specific range, polar vortex disruption becomes highly likely. That's a high-dimensional correlation that no human could intuitively grasp. But a neural network could learn it from the data. And once it learns it, it could issue warnings. Early alerts that a solar storm in the next 24 to 48 hours might trigger atmospheric instability. That kind of prediction, even with significant uncertainty, would be valuable. Power companies could prepare. Emergency managers could pre-position resources. People in vulnerable regions could stock up on supplies. The prediction doesn't have to be perfect to be useful. It just has to be better than nothing. There's also the potential for AI to identify dangerous alignments, specific combinations of solar activity and atmospheric state that are particularly risky. Not all solar storms affect weather. Most probably don't. But under certain conditions, when the atmosphere is already poised at a critical point, and a solar storm provides the right kind of perturbation, the impacts could be amplified. And AI could learn to recognize those conditions. It could flag situations where the risk is elevated, even if the solar storm itself doesn't look particularly extreme. That's a level of nuance that traditional forecasting struggles with. Meteorologists issue winter storm warnings based on predicted snow amounts and temperatures. Space weather forecasters issue geomagnetic storm warnings based on solar wind parameters. But nobody is issuing warnings based on the combination of both. An AI could do that. Of course, there are challenges. AI models are only as good as their training data, and the training data for solar weather coupling is limited. We've only had comprehensive satellite observations of space weather for a few decades. That's not a huge sample size for machine learning, especially when you're looking for rare, extreme events. The January 2026 storm might be one of only a handful of comparable events in the modern record. You can't train a robust neural network on 5 data points. You need hundreds, ideally thousands. So any AI model trained today would be tentative, prone to overfitting, uncertain. But that might still be better than the current situation, where we're not looking for these connections at all. There's also the interpretability problem. Neural networks are often black boxes. They can tell you what they predict, but they can't always tell you why. If an AI issues a warning that a solar storm is likely to amplify an ongoing atmospheric disturbance, scientists will want to know the physical reasoning. They'll want to understand the mechanism. And the AI might not be able to provide that. It might just say, this pattern occurred before and was followed by extreme weather, so it's likely to happen again. That lack of mechanistic understanding makes some scientists uncomfortable, and rightly so. Prediction without understanding is useful, but it's not science. Science seeks to explain, not just to forecast. So ideally, AI predictions would be used as a tool to guide human inquiry, highlighting correlations that deserve closer investigation rather than replacing traditional research. Winter 2026, viewed through this lens, is a perfect case study. It's an event that future AI systems will analyze obsessively. The combination of a major solar storm, a polar vortex disruption, and widespread extreme weather all occurring simultaneously is exactly the kind of pattern that machine learning algorithms are designed to detect. If we can assemble the data properly, if we can train models to look at these multi-domain interactions, January 2026 might become a landmark event. Not because it was the most extreme storm ever recorded, but because it was the event that forced us to start taking solar weather coupling seriously. It was the alarm bell that finally got loud enough to be heard. But here's the uncomfortable part. Even with AI, even with perfect data and sophisticated models, we might still struggle to predict these events reliably. Chaotic systems are inherently unpredictable beyond certain timescales. The atmosphere is chaotic. The sun is chaotic. The coupling between them is doubly chaotic. There might be fundamental limits to how far in advance we can issue warnings. We might be stuck with a 12 to 24 hour prediction window, enough time to brace for impact, but not enough to fundamentally change outcomes. And that means we need to shift our thinking from prediction to resilience. We need infrastructure that can withstand extreme space weather and extreme terrestrial weather simultaneously. We need redundant systems. We need community-level preparedness. We need a culture that understands these risks and doesn't wait for perfect predictions before taking action. So here's the final question, the one that ties everything together. Are we ready to accept that Earth's weather isn't self-contained? Are we ready to admit that the boundary between space and atmosphere is more permeable than we thought? Are we willing to fund the research, build the monitoring networks, and develop the models that would let us understand and predict these interactions? Because the alternative is to keep treating weather and space weather as separate domains, to keep missing the connections, to keep being surprised when extreme events align in ways we didn't expect. We can keep pretending that a solar storm 93 million miles away can't possibly affect the snow falling outside your window. Or we can look at the data from January 2026, look at the timing and the impacts and the anomalies, and admit that maybe, just maybe, we've been missing something important. The storms outside your window, the ice coating your streets, the power outages and infrastructure failures, they might not have started in the Arctic after all. They might have started 8 light minutes away on the surface of the sun when a long-duration X-class flare pumped radiation into space and set off a chain of events that cascaded through the magnetosphere, through the upper atmosphere, through the stratosphere, and finally down into the weather systems we experience on the ground. The sun didn't create winter, but it might have amplified it in ways we're only beginning to understand. And if that's true, if the connection is real, then every winter forecast, every polar vortex prediction, every infrastructure resilience plan needs to be rewritten with space weather in mind. Because the next time a major solar storm hits during an unstable atmospheric pattern, we might not be as lucky as we were in January. The polarity might align differently. The timing might be worse, the impacts might be catastrophic. And when that happens, the question won't be whether space weather affects terrestrial weather. The question will be why we didn't take it seriously sooner. Why we ignored the warning signs. Why we let institutional inertia and disciplinary silos blind us to connections that were there all along, waiting to be seen. Winter 2026 was a test. We didn't pass. But we got data, we got evidence, we got a glimpse of how our planet responds when the sun decides to remind us who's really in charge. And that glimpse, unsettling as it is, might be exactly what we need to prepare for what comes next.